I love that they came prepared with cameras. I just love it. It's brilliant. Lots of people come in here, yeah, you can't really see much, frankly. This room is a little difficult because we can't actually see a lot of what we want to see, which is behind me. Okay. Yeah, get a few pictures. One of the great things about this room is that you can see sort of a beam line. I mean, this is the pipe where the nuclei will actually pass through. These are the magnets that are going to continually focus that beam as it passes through. Remember, a beam of nuclei is actually a lot of charged particles. You need to constantly be focusing and steering it to keep them going in the right direction. Otherwise, it doesn't become a beam, it becomes a spray, and you lose them all. So, this is going to focus our beam as it passes through. You're seeing all the same systems we've seen before. Here's power, here's control. These are pipes for the liquid nitrogen and liquid helium, cryogenics. And you're hearing the vacuum pumps. There it is right there. So all these systems have to be kept running. Otherwise you can't do it.
I have two questions. One,
shoot.
Is that where the...
That's actually where the nuclei would pass through.
Yeah. Does the moon affect like the pipes? Is it big enough where the moon's gravity would affect the pipes?
Oh, no, no. Nope. Ultimately, I mean, we are very sensitive to position here. I mean, all these things have to be placed sometimes to within one 1/1000th of an inch or so. Yeah, so it's pretty small, but it's all well put together. I mean, earthquakes would be a bigger deal. And you know how many earthquakes we get here? Not that many. One great reason to do nuclear science in Michigan. There you go. So, take that, California. Okay, so this room is called the gas stopping station. We actually are going to have 2 gas stopping stations in here. And this is just kind of one stop on the way to your experiment. There's no detectors in here, but you have places where you can stop their beam. Because there are some experiments you want to do, you can't have the nucleus going half the speed of light. For instance, try to weigh yourself by driving over the scale at half the speed of light. That would be impressive, A, and B, you can't do it. So, we need to actually stop the nuclei before we can measure their mass. So we actually have in here one gas stopper, and another one's going to be installed. To stop a beam of nuclei, you, instead of have them passing through a vacuum, you'll introduce a helium gas. A fairly thin helium gas, but as the nuclei pass through, they're going to be bouncing off individual helium atoms, which of course are very, very light, very low mass, so they will slow these rare isotopes down very gently. That's kind of like covering the highway with pillows. It will stop the car eventually, and in theory not damage the car or its contents. Yes?
Is this connected to the Mona Lisa?
Actually, the Mona Lisa is here, so the Mona Lisa is one branch, and this is another branch. So it depends on where you want to go, ultimately.
Is that like one of the magnets that keep it centered?
That is a turn.
Oh, that's what I meant.
That's just, I'm going to turn the beam. These keep them centered. That one says, I want to turn right. And you need, in fact, we'll talk about this magnet while we're standing here. What you're seeing is the outer steel shell. It's called a yoke. It's several inches of steel that we use to kind of contain and focus the magnetic field. Deep inside there are coils of that superconducting wire I showed you. And those are carrying a lot of current when they're on. Not right now, but they would carry several hundred amps of current. They'd be bathed in liquid helium, so they'd be superconducting. And then there'd be a layer of liquid nitrogen around that as an insulator. Because as heat penetrates, it'll boil off liquid nitrogen, which is cheap, and not the liquid helium, which is expensive. So all the magnets you're seeing are essentially these same components. And we built almost all of them ourselves here in this building. And you will see that before we're done. Now, if you want to stop nuclei, you pass them through this helium gas, and it's going to slow them down very gently. Plus, helium is a noble gas, so it's not going to interact chemically with your nuclei, so you'll be able to re-extract your rare isotope at the end. So you bring it down to essentially no energy, you extract it, and then you can send it off to do a precision measurement somewhere where your nucleus is at very, very low energy. So you can do that with a helium gas, but of course some nuclei would require a lot larger amount of helium gas to stop from half the speed of light down to 0. Well, I don't want to build a really, really, really long container of helium gas. Like, I'm limited by the street over here. So we are actually building now a new kind of gas stopper that nobody's ever tried before. Now, you know how the cyclotron works. I showed you. basically nuclei are injected, they go in a circle because of the high magnetic field, and they end up spiraling out because we're applying higher and higher electric field, so they accelerate, come to the edge, and shoot out. We're going to build a cyclotron that will go over there. It'll be up on end. Nuclei will come in at the edge, already traveling half the speed of light. There won't be any electric field in here, just a magnetic field, keep it going in a circle. But instead of a vacuum, in that cyclotron will be a helium gas. As the nuclei pass through the helium gas, they will slow, spiraling in, and be extracted out the middle. We are building a reverse cyclotron for this laboratory. Oh, well, it's got to be a really short amount of time, less than a second. In fact, all these experiments are essentially limited by how fast can I do what I need to do, because I'm trying to study a nucleus. So it's tricky. I've got to accelerate smash. After I smash, my clock's ticking. I need to stop the nucleus and then extract it, put it over to my detector, and measure it. We have measured the mass of lithium-11. Lithium-11 has a half-life of about 10 milliseconds. And a lot of what we do is making sure, can I do this faster? How can I make this work? It's amazing. So anyway, we're building a reverse cyclotron. Nobody's ever done this before. We are making it up. You know?
How about just pressurizing the helium gas?
So basically there is a limit, because the larger density of the helium, you end up getting fewer nuclei out the other end. That's the problem. So you want to do it under a very light. It's the same reason why we don't have a thicker beryllium foil. We get more interaction events, but we're also going to lose a lot of our nuclei. So it's a balancing act that's very difficult. But yeah, excellent point. You know, I just want more helium, right? Well, the beauty of a cyclotron is you get a really long path length in a very small, compact package. So it's great. It's great. I'm telling you, this is where the action is. I'll show you, before we are done, I will be able to show you pieces of the cyclotron gas stopper. It's being put together right now. Excellent, excellent stuff.
Well, I have to take tests.
Sadly, yes. Hey, you got to do all this training. You have to get, ladder safety training, radiation safety training, stop work order. Very important stuff. So anyway, this is where we will stop the nuclei. Another good thing to look at while you're here, the roof is off, part of it anyway, so you can see into the room, the big room that we've been in this tour, and will continue to be in for most of it. So really, we're in a smaller concrete bunker to contain the radiation that's within this much larger room. And I'll show you why we have one large room before we're done.
Practical question, is there an overhead crane in there?
Yes, and that's why. See, you just stole my...
Sorry.
That's okay. That's okay. Good guess. Hey, I encourage that. Yes. So that's what we have to look forward to. Good. Any other questions about gas stopping? It's great stuff. Now I'll show you what we actually do with the nuclei that we've stopped. It's over here.